Okay, okay guys, so this one we have done it. AM, large carrier amplitude modulation, large carrier, or double sideband. Large carrier, when we said double sideband, because we have upper sideband, if you remember the spectrum, and lower sideband, and in between we have the carrier frequency. All right, then this one also we call it double sideband. Why double sideband? Also, we will, as we will see from the spectrum, when we will draw the spectrum, then the spectrum also will be like a double sideband. All right, double sideband, like this signal. All right, so we have upper sideband, all right, and LSB, which is lower sideband. All right, so when we said double sideband, so that means we have upper sideband and lower sideband. Suppressed carrier, that means we don't have any carrier in between. All right, we don't have any carrier in between. We're gonna suppress, we're gonna remove the carrier. All right, so let's try to discover this type of amplitude modulation. All right, as we said that the carrier component in AM, again, when I said AM, that means large carrier, I mean, does not convey any information and may be removed to attain what we call it higher power efficiency. All right, because in large carrier, the power actually is distributed between upper, lower, and the carrier itself. And you remember, if we, I mean, let the modulation index equal to 1, then the maximum will be 1/3 of the total power. All right, 1/3 of the total power. So in this case, if we removed the carrier, then if we removed the carrier, then still we have, I mean, better what we call it power efficiency. All right, power efficiency will be better in terms of dealing with double sideband suppressed carrier modulation compared to double sideband large carrier modulation. So this one we call it double sideband suppressed carrier. All right, double sideband suppressed carrier, because we are going to remove the carrier. All right. So let's see how we can do that. For example, if we have a carrier, consider the carrier. This is the carrier signal, S sub C, C from carrier. This one continuous time, we have the amplitude, cosine, omega sub CT, and we have modulated by a signal, sinusoidal signal, which is this one modulating signal, SM, equal to A sub M cosine omega M T. So what we need to do, product of these two signals, you can see this one, the modulated signal S of T, S sub M, which is the modulating signal times the carrier signal. You can now see this one, cosine omega C, which is the carrier frequency, and cosine omega M, which is the frequency for the message. Okay, and this one again from the relation, we have cosine times cosine, then will be half cosine plus and cosine minus. All right, so we have AC AM divided by 2. This 2 comes from the relationship multiplication of 2 cosine. Cosine A times cosine B, the result will be half cosine A plus B plus half cosine A minus B. So normally we make it in terms of omega C plus omega M and omega C minus omega M. The reason why, because this one is much higher than this one. Okay, and you can see here, this one, the positive part will represent the upper sideband. This one will be upper sideband, and this one minus will be lower sideband. We don't have any carrier. We don't have any, I mean, the carrier in its as an independent, we don't have it here, because if you would like to compare this one with large carrier, we have same this one, but here we have A sub C cosine omega C T plus this one. All right. So the main difference between, you can compare the mathematical formulation. This one suppressed carrier compared to large carrier. This is suppressed carriers. We have 2 terms, And in large carrier, we have one more, which is the carrier frequency as an independent signal. All right, independent signal. So that we, in this particular scenario, we remove this term. We have only this one and this one, upper sideband and lower sideband. Definitely we have carrier signal. Definitely we have carrier signal, but we suppressed this one, which is only carrier, pure carrier. There is no modulating signal. There is no omega m in this term. Okay. Then this is the block diagram for what you call it, double sideband suppressed carrier. This is the modulating signal. Modulating signal. All right, and this is the carrier signal. All right, and here we have multiplier, and this is the output. All right, multiplier, and we have the output. Then this is the modulated signal. Modulated signal, A sub c cosine omega ct times, all right, you have multiplier am cosine omega m t. All right, and if you would like to draw the spectrum, then we can do that very straightforward. Here we have a formula, all right, relationship, one multiplying cosine A cosine B, same that we have done it in previous slide, this one. Then from here you can refer to Fourier transform table in order to choose the property. Again, we have only one property that related to modulation property, will be something like what we have done it also in large carrier. Okay, so in reality this one will be 4, all right, because 2 actually from time domain, as we can see from continuous time previous slide, and when we apply Fourier transform we have another half, then will be 4. Okay. So this is the only property that we need to consider in amplitude modulation. All right, so this is the spectrum, how it looks like. Frequency domain, the spectrum, this is the original message or modulating signal. Okay, you can see the bandwidth is, let's say, B, and this is the hello, yes, is there any question? Okay, and this is the result, the modulated signal. As we can see, we have USB, which is upper side band, and we have LSB, which is lower side band, and we don't have carrier. All right, we don't have carrier in between as an independent signal. All right, so the bandwidth is still same compared to double sideband LC large carrier. The bandwidth same. All right, we transmitted bandwidth B and we receive 2B, so the bandwidth actually is twice the modulating signal bandwidth. All right, twice the modulating signal bandwidth. And here the main advantage of this one, all the transmitted power is contained in 2 sidebands, no carrier present. All right, no carrier present, so the power will be here and here, upper sideband and lower sideband, and definitely the power efficiency will be better compared to double sideband large carrier. Okay, here's another note. Upper sideband display the positive component of the modulating signal, and lower sideband display the negative component of modulating signal. All right, so now again, similar to what we have done in double sideband large carrier, we said that we have generator and detector. All right, we need to generate and also we need to detect. When I said we need to generate, that means it's a modulation, and when we said that we need to detect, that means it's demodulation, generation at the transmitter and detection at the receiver. All right, so again, for this type, which is double sideband suppressed carrier, also we need to generate the modulated signal, and also we need to detect modulating signal. All right, so again we have some technique. we have some technique. The simplest technique actually is we use what we call it, the balance modulator. All right, balanced modulator. Okay, balance modulator. This is the block diagram. This is the block diagram for what we call it, balanced modulator. All right, balanced modulator. Let's have a look to this block diagram and see what we can do with the generation of double sideband suppressed carrier. Here we have modulating signal, all right, information signal, message, all right, and here we have two level. This one, the original signal, SN, same modulating signal, message signal. Here we have inverter, all right, here we have inverter, so the result will be minus Sm of T, all right, minus Sm of T. And after that, we have normal amplitude modulator. Here it's modulator. When I said modulator, that means a modulator. You need to multiply this one by this one. All right, all right. And this one here we have local oscillator or a frequency generator or carrier generator in order to generate carrier. So we have two parts, two level. This one, the carrier, A sub C cosine omega CT goes for this level, and same carrier, A sub C cosine omega CT goes for the lower level. Okay, so here we have S1 of T, and here we have S2 of T. So we need to perform summation. Here we have summer or other component or other hardware component. So the result will be double sideband suppress carrier. All right, double sideband suppress carrier. Let's try to see if there's any mathematical formulation to see how we can do that. For example, here we have all right. Okay, so this is S1 of T. S1 of T, which is AM signal, and S2 of T, you can see the main difference, this one plus this one minus, this one plus, and this one minus. So the output S of T will be S1 of T minus S2 of T. All right, minus S2 of T, and this one is very straightforward, very simple. You can multiply this one by, for example, you have AC cosine, this one omega CT, and you multiply this one by this one, and you say multiplication with this one, and you subtract both signal. You will see that we have only, all right, we will have only 2 M A sub C cosine omega MT cosine omega CT. This one actually is full AM. If you remember, this one, the general expression for double side band large carrier. All right, this one, the general expression, mathematical expression for double side band large carrier. All right, double side band large carrier. All right, and this one after we invert, then if you multiply all together and you this one minus S2, definitely here we have A sub C in positive. After we apply the negative here, the minus, so all the carrier signal will be cancelled. All right, so we have only 2 M A sub C cosine omega MT cosine omega sub C T. Okay, and this one definitely can be ignored. All right, this two can be ignored. Then the generated result will be AM cosine omega MT AC cosine omega CT. Okay, which is, I mean, double sideband suppressed carrier. All right, double sideband suppressed carrier. As you can see, I mean, I would like to repeat it again and again. In this chapter, we have only cosine times cosine. All right, maximum we can reach sine times cosine. The remaining will, I mean, we're gonna repeat same concept again and again and again. Either multiplier. Once we multiply the carrier with modulating signal, maybe we have some others, we have some subtractor, or we have some phase shift, but still we are dealing with multiplication of two sinusoidal signals, all right, multiplication of two sinusoidal signals. So if you understand one technique, the remaining will be just a repeated versions of that particular technique, all right? And the other technique, actually, we call it the, in terms of detection or demodulation, we have what we call it the coherent detection, all right, coherent detection, or what you call it the synchronized detection. Okay, so here we have very important note. Since the carrier is suppressed, that means we don't have carrier as independent signal, the envelope detector no longer represents the modulating signal, all right, no longer represent the modulating signal. Hence envelope detector, which is type of non-coherent detection, cannot be used. When I said coherent detection, that means synchronized detection. Synchronized detection. I will explain afterward once we, reach to this block diagram, all right? So previously, double sideband large carrier, it was non-coherent detection, all right? Non-coherent detection, because we have only the carrier and the carrier is there. So, no need to use some synchronized detection. But in this particular case, non-coherent detection, since we removed the carrier, then non-coherent detection cannot be used in this particular type of amplitude modulation. All right. So let's see the block diagram of this one, coherent detector of double sideband suppressed carrier or product detector. So here we have double sideband suppressed carrier signal. Double sideband suppressed carrier signal. What's the double sideband suppressed carrier signal? This one, all right, you can see this is the double sideband suppressed carrier signal, okay? Then what else we have? Here we have local oscillator, all right, local oscillator. The main function of this local oscillator is used to generate carrier frequency, and this carrier frequency should be synchronized with transmitter and receiver at both phase and frequency. So that means same phase with the transmitter and same frequency with the transmitter. And definitely this one will be a little bit difficult, all right, a little bit difficult, all right? So that's why we call it coherent detection. When we said coherent detection, that means synchronized detection. This one actually is very common in communication, coherent and non-coherent, all right? So if we said coherent detection or coherent detector, that means you need to think in terms of some local, not only local oscillator, but a special local oscillator in order to generate or in order to be synchronized with both transmitter and receiver with both frequency and phase, all right, with both frequency and phase. You can see this one, carrier frequency, which is cosine omega sub c. Then we have multiplier, and after that we have low pass filter, all right, after that we have low pass filter. What is, our desired when we said detector, that means I need to receive this one receiver here, right, this one receiver, then I need to receive SM, all right, SM of t, all right, SM of t. So let's have a look to this one. So this is actually V of t. When I said this is V of t, this is the output here, V of t, after V of t. Okay. Then we have double sideband suppressed carrier signal, which is this one, S of t cosine all right, cosine omega ct, S of t, if you remember. This one, S of t, you can see this one, S of t. Okay, then S of t cosine omega ct from local oscillator, from local or oscillator or frequency generator, or whatever, but normally we call it local oscillator, but we have here special local oscillator in coherent detection. Since we said coherent detection, that means we have a special local oscillator, all right. So if we multiply this one cosine, then we will have A sub c, which is the amplitude of carrier, times the modulating signal, message signal. We have cosine squared omega c. Why? Because here we have cosine omega c t, and we multiply by local oscillator or by the carrier, which is cosine omega c t. So the result will be, this one actually is Sm. All right, this one all A sub m cosine omega t. I can replace it by this one. You can see Sm of t. Then I will reach to this one cosine squared omega c t. All right. Okay. Then from relation, trig relation, cosine, this one cosine squared will be this one cosine squared. I can rewrite it 1 over 2. All right. 1 plus cosine 2 omega c t. This one from relation. All right, this one from a relation. Then I have here, this cosine squared can be replaced by this one. Then what I have, A sub c sigma s of m divided by 2 multiplied by 1. Then I have this part. And again, this one, all right, A sub c multiplied by this one cosine 2 omega c t. All right, cosine 2 omega c t. So now I have two terms, 1 and 2. So which one will pass through the low pass filter? Which one will pass through the low pass filter? Definitely this one. All right, this one. Okay, this one we have some higher frequency, which is 2 omega sub c. All right, 2 omega c. Then this one definitely going to cancel out from the low pass filter. Then I have only V out here, the output of low pass filter, A sub c Sm of t divided by 2. All right, divided by 2, which is actually, it's a copy of the transmitted signal. It is a copy of transmitted signal. I need to receive definitely Sm, all right, Sm of t, all right, not divided by 2. But this is actually is acceptable in communication, because definitely before we reach to receiver, we have some amplifier. All right, we have some amplifier, because it's, I mean, common in communication to have some attenuation along the way from the transmitter to receiver. So we have amplifier, then we can amplify this message to level of the original transmitted signal. All right, so this is the coherent detector of double sideband suppress carrier. Okay guys, any questions so far? No question? All right. Okay, then let's continue. This one, all right, for proper signal recovery, it's necessary to ensure that, yeah, this one actually, it's in AM, as I mentioned. AM, as I mentioned. This one should be greater than this one. All right. The carrier frequency should be greater than the frequency of the modulating signal. And for coherent detection, required detection of double sideband suppressed carrier, it is also necessary to have synchronization, all right, in both frequency and phase, as I mentioned, in local oscillator. All right, in local oscillator, normally this special type of local oscillator is used to to generate carrier frequency, and that particular carrier frequency should be synchronized. All right, synchronized, yeah, synchronization, synchronized with transmitter and receiver at both frequency and phase. Okay, so both the correct phase and the frequency must be known in order to demodulate, or in order to detect, or in order to receive double sideband suppressed carrier waveforms. Okay, so now here we'll take an example. What will happen if we have some lack of phase synchronization in coherent detection? All right, lack of phase. So suppose that this is the received signal, double sideband suppressed carrier. Compared to previous one, here we have this one. All right, so if you remove this one, will be original double sideband suppressed carrier, but we assume that we have some phase, all right, some phase, which is distortion. So what will happen? What will happen? Again, this is the double sideband suppressed carrier, all right, double sideband suppressed carrier, which is, all right, this one, all right, this is the received one, okay, and we need to multiply by local oscillator. All right, let's show you the block diagram. All right, we assume that the received one here, we have some phase, all right, some phase, all right. Then we have to multiply with local oscillator, same procedure, what we have done here, okay. Then what we'll have, you can see this one is with a, all right, then multiply by the carrier frequency, then we will reach to this, cosine times cosine, same cosine A, cosine B, then we'll reach to this one, A sub C divided by 2 as M of T. We have cosine 2 omega CT plus theta, and also we have cosine theta. All right, compared to the previous one, we don't have this one. All right, we don't have this term, and also we don't have theta in this case. Okay, then what will happen after that? Then the output of low pass filter will be, the output for low pass filter definitely will, this one will be high frequency, 2 omega sub C. All right, 2 omega sub C. The output from low pass filter will be only this one. Okay, only this one. All right, then this is the output after low pass filter stage, but we want only this one. We want only this one. We don't want this one. What's the worst scenario? What's the worst case scenario of this one? If we have theta pi over 2, then giving rise to 0, no output at the receiver. All right, no output. No output if this, equal to pi over 2. So this is actually the problem, right? This is the problem by using coherent detection, all right? By using coherent detection, we need to make sure that the local oscillator generates really, carrier signal or carrier frequency, and that should be synchronized, all right? Synchronized with transmitter, receiver at both frequency and phase. So this is the problem actually if we have phase, all right? If we have some phase distortion, and also another scenario, we have some lack of frequency, all right? Lack of frequency synchronization in coherent detection. Same procedure, but we assume here that this is the double sideband suppressed carrier, but here we assume that we have some frequency, all right? Some frequency, delta W, that means some variation, plus, minus, all right? Then this is the, once I multiply this one by carrier signal, again, by local oscillator, again, this one cosine A, cosine B, you can apply same trig relation, all right, which is half cosine A plus B and cosine A minus B, all right? So this is the result signal. Then after low pass filter, definitely I'll take this one from low pass filter, all right, low pass filter, and this one gonna cancelled by low pass filter because 2 omega C, which is high frequency, 2 omega C. Then again, this is the received, and I want only this one. I don't want any cosine attached with my original message, right? So that's the recovered baseband information signal will vary sinusoidally according to cosine omega t, which is definitely this one, unwanted scenario. This is unwanted scenario. So all these actually problems happened when we have coherent detection, all right? When we have coherent detection here, coherent detection or demodulation or recovering the original signal. This is the block diagram. We have to use some special local oscillator to make sure that both transmitter and receiver are synchronized synchronized at both frequency and phase. So if we have any phase distortion like this one, you can see we cannot receive the original message. And also if we have any frequency, all right, distortion. Also, we cannot receive the original signal. So that's why it's, I mean, this is the what we call it, the disadvantages of the side effect of what we call it the coherent detection in amplitude modulation. All right, how we can recover this problem? Do we have some technique that we can recover these problems? The answer is yes. All right, the answer is yes. We can use this block diagram. All right, so we're gonna solve the problem, but we have to pay more price because the cost gonna increase. The cost gonna increase again and again by using, I mean, series of circuits in order to make synchronized between carrier frequency and modulating signal and at receiver modulated signal. All right, so this is what we call it, the frequency synchronizer, the block diagram of frequency synchronizer. Okay, block diagram of frequency synchronizer is used to make sure normally we use this one to make sure that there is no phase and frequency distortion at the carrier, all right, carrier signal. Okay, so this is the block diagram. Here we have double sideband suppressed carrier signal, double sideband suppressed carrier signal. Here we have nonlinear device similar to the device that we have used in double sideband large carrier, and here we have narrow band pass filter, all right, band pass filter, and here we have frequency divider, all right, frequency divider. We will see after we derive why it's divided by 2. And this one here we have another, what we call it, phase locked loop. This one phase, all right, lock loop, PLL, all right, phase lock loop. This one actually is used to track the phase of input signal, all right, and to minimize any phase error, if any, all right. If there's any phase error, then this device, this electronic circuit, which is electronic circuit that we can design, is used to minimize phase error to local oscillator, all right, phase error to local oscillator. That means we are here until this one, we need just to generate local oscillator. So that means this one, all the circuits here just before local oscillator. The output here, we need to make it cosine, all right, cosine omega c t only. There is no phase and there is no frequency, no phase and no frequency. So what we have done here, all this complicated circuit in order to generate what we call it the synchronized local oscillator, synchronized local oscillator with the modulating signal. Okay, so this one, the phase lock loop, is used to track the phase of input signal and also to minimize phase error to local oscillator. That means the phase will be at its minimum once reached to. Yes, Harish?
Yes, sir. Excuse me.
Yes.
You said synchronized local oscillator. I know what does synchronization mean, but I don't understand what the oscillator would do when you say synchronized oscillator.
All right, as I mentioned, local oscillator actually is to generate carrier frequency. You can see here, this is the local oscillator. All right, this is local oscillator.
Yes.
All right, this is local oscillator that normally generate carrier frequency, cosine, okay, omega c t. All right, cosine omega c t. Am I right? So in this particular scenario, we said we don't have the carrier as an independent signal, so that's why we need to do some non-coherent detection cannot be used. So we need to use some coherent detection, synchronized. So that means both the local oscillator, the carrier frequency must be synchronized with the modulating signal. Same phase, if any, and same frequency. All right? If there's some distortion in phase and frequency, as I mentioned here, if there is some lack of phase synchronization, that means here we have some phase, all right, distortion, all right, some phase distortion, then definitely we cannot receive the modulating signal. And also if we have some frequency distortion, then also we cannot recover the original signal. The received signal definitely will be varies sinusoidally with this one distortion in terms of frequency or in terms of phase. So that's why we need to minimize if there is any phase shift, all right, or if there any frequency variation, we need to minimize before we reach to local oscillator, all right, before we reach to local oscillator. So that's why both will be same. If I multiply, for example, this is the modulating signal cosine omega ct, the local oscillator definitely will generate cosine omega ct. But if I have any phase here, distortion, all right, if I have any distortion, this one, instead of cosine omega ct, I have cosine plus some phase, all right? So this one, the phase loop will minimize this one, all must remove this one before we reach to local oscillator in order to make, ready to receive the original signal or the modulating signal. Is that clear, Harish?
Yes, sir. Yeah, definitely.
Right. Okay. Then all right, yeah. So this one again, this one actually is electronic circuits, the phase lock loop, all right, that normally used to minimize the phase, all right, minimize the phase error, before what we call it, before we reach to local oscillator, all right, before we reach to local oscillator. Okay, so in terms of mathematically speaking, let's say the baseband signal, all right, the modulating signal, am cosine omega mt, and the received double sideband suppressed carrier, this one, all right, suppressed carrier is this one. Then if we pass through this one, the nonlinear device, we squared, all right, everything's here, a squared, am squared, cosine omega squared, and cosine omega c squared. Okay, then also by using the relation, cosine squared will be 1 over 2, 1 plus cosine 2 omega and 1 plus cosine 2 omega c. So since we have half from here, this term, and half from this cosine square, we have divided by 4. All right, this is the relation. This is the relation. Cosine squared will be half. All right, 1 plus cosine 2, let's say omega m t. All right, so another cosine squared, which is we have half, so half we have over 4, and 1 plus cosine 2 omega mt, 1 plus cosine 2 omega ct, and by rearrange, all right, by multiply, then we can reach to this equation. All right, so after that we need to pass through bandpass filter. The filter, for example, is 2 f sub c or 2 omega c, then we will receive only this one. All right, we'll receive only this one. This is a constant. Okay, now we need what we need actually. All right, what we need cosine omega ct, not 2. As you can see, the output here, the output from this circuit will be cosine 2. All right, and I need, in order to make it, synchronize with local oscillator, I need cosine omega ct. All right, so that's why I have what we call the frequency divider. All right, frequency divider by 2, then I have to apply the frequency divider. This is the output of frequency divider. All right, output of frequency divider will be cosine omega c t, and this is k constant, can be replaced by this the amplitude of the carrier signal and the amplitude of modulating signal. All right, so this is all what we need to do for synchronization. All right, all what we need to do for synchronization, extra synchronization circuit is required to detect the phase and frequency, if any, by providing synchronous local oscillation, oscillator carrier signal to the receiver. All right. And definitely we have disadvantages of using this complicated circuit. Require a precise frequency and phase synchronization, which is difficult to achieve, and also more expensive due to additional synchronizing circuits. All right, this one is really will be, I mean, double or more than compared to, in terms of cost, compared to double sideband large carrier. All right, compared to double sideband large carrier. Okay, so now we can compare, actually, once we've done this one, we can compare between large carrier, what's the main advantages and disadvantages of large carrier, and compared to advantages and disadvantages of suppressed carrier. All right, so we have a carrier, but in price. All right, we can, I mean, design very simple circuit at receiver in order to demodulate. But in this particular case, we remove the carrier, we improve the power. All right, power efficiency gonna improve, but you can see the price that you need to pay in design really complicated electronic circuit. And not only complicated, but also in terms of frequency and phase synchronization will be very difficult to achieve. Okay, so this one actually the second technique. The last technique that I will explain, we have actually two more techniques. This one, single sideband modulation, and stagel sideband, single band or sideband. I will leave that technique actually to you as a self study. I mean, once you have learned this one, then you can easy for you to I mean, grab the idea of vestigial. So this is actually, it's the third technique that we call it single sideband modulation. So technique number one, it was double sideband large carrier. The second type, we call it double sideband suppressed carrier. So we keep talking about double sideband, double sideband, double sideband, right? So the question that is, I mean, that might arise here, can we, I mean, we have technique only single sideband, I mean, either upper or lower, in order to provide more bandwidth, or in order to save the bandwidth, or in order to save the spectrum? The answer actually is yes, by using what you call it single sideband modulation, or SSB technique. Okay, so you can see this one, full AM, large carrier, and double sideband suppressed carrier. The bandwidth of modulating signal will be twice of the modulating signal. All right, the bandwidth will be 2W. So one half the transmission bandwidth is occupied by upper sideband, and the last one by lower sideband. Okay, so the basic information is transmitted twice, once in each sideband. All right, upper and lower. And definitely, if we can focus only on one band, all right, and remove the other, then definitely we can save the spectrum. We can send more signals. All right, we can send more signals, because the bandwidth for modulated signal will be same as the bandwidth of the transmitted signal. Okay, there is no wastage in terms of bandwidth or spectrum. So one sideband can be suppressed, and the remaining sideband is called single sideband suppressed carrier. All right, single sideband suppressed carrier. Either we call it SSB or SSSC, single sideband suppressed carrier. All right, so on this technique, we're going to take only one side, only one side. Okay, so this is the bandwidth of the modulating signal. All right, modulating signal. And this is the bandwidth of, if you remember, double sideband, we have like that. All right, double sideband, we have F sub C plus Fm, and here we have F sub C minus Fm. All right, so that's why we call it upper sideband and lower sideband. While in this particular scenario, we will have only one side. We will focus, for example, upper sideband only, upper sideband only. Okay, so by transmitting only either upper sideband or lower sideband, the original baseband message can still be recovered. Again, we have some generation and detection. And the power transmitted will be this one. All right, this one actually you need it in the tutorial. For example, the question that related to power in single sideband, you need to use this formula, for example, okay, in order to calculate the power. What else? The advantages actually of single sideband, it's very obvious. We can provide, we can save the frequency, we can save the bandwidth. So that means more signal can be transmitted, all right? More signal can be transmitted in a given frequency range. While in double sideband, either large carrier or suppressed carrier, definitely the overlapping will take place. That means overlapping between adjacent frequency will be very high compared to single sideband suppressed carrier. So in terms of generation, we have filter method. All right, in terms of generation, we have filter method. This is M of T, the modulating signal. This is carrier signal, and this is double sideband. Right, double sideband signal, same to what we have done previously. And here we have what we call it sideband filter. Sideband filter. This is the frequency response of that particular filter, sideband filter, and after filter we have what you call it the single sideband. All right, single sideband. So this is the block diagram for single sideband modulation. All right, so now we need to generate. Okay, so this one actually we got some problem. All right, it's not an easy. It's not like that. We have actually, it's really serious problem when we dealing with sideband filter. We're dealing with sideband filter. Definitely this is the common, all right? This is the most commonly used method of generating single sideband, all right? Single sideband. But so as we can see, in this method, the double sideband suppressed carrier signal is passed through sharp cutoff filter. This one actually is very special selective filter. All right, special selective filter, and I will explain the reason why. Okay, so double sideband suppressed carrier signal will pass through this filter, all right, or what you call it the sharp cutoff filter, to eliminate the undesired sideband. All right, to eliminate the undesired sideband, either lower or higher. All right, so this is double sideband. If I use filter, but definitely this one, it's not a real, all right, it's not a real spectrum, because in order to obtain, for example, let's say upper sideband, in order to obtain upper sideband, so the filter should pass all components above this one, all components above F sub C, and definitely attenuated or remove all the components which is below F sub C. So such operation, I mean, if I would like to remove this one, all the components above the carrier frequency or above F sub C, such an operation require a really ideal filter, which is unrealizable. All right, we cannot reach to ideal filter. We cannot design ideal filter. Okay, so this one actually, in terms of certain sense, this one will be like an impossible to adopt. But so that's why we have limited application for single sideband, limited application. What we need to do, only if we can use this one, the sideband filter, only we have some separation. If we have some separation between upper sideband and lower sideband, then this filter will be realizable. Only this filter will be realizable. But in most scenarios, if you remember when we draw our spectrum, we make it like that. All right, the signal will be like that. All right, there is no much separation. There is no much separation between upper and lower. All right, there is no separation between upper and lower. So here we put separation. We put separation just to simplify. All right, just to simplify. So if there is any signal that comes with some separation in a frequency domain representation, then this technique will be we can adopt this technique, and otherwise it's very difficult to adopt that technique. So when or where we can adopt this technique, this one actually can be adopted in voice signal. All right, voice signal. You can see here voice and music signal. Voice and music signal shows some. If we'd like to draw, for example, the frequency response of voice, and there is no much frequencies at zero, all right, no much frequencies at zeros, all right, and even the signal, the frequency below 300 hertz, if we remove this frequency from voice or music, this one actually will not affect on the quality of the signal. All right, so that's why single sideband required some, all right, required some application where there is some separation. All right, there is some separation between upper and lower sideband in frequency domain representation. If we have that separation, then single sideband will be the best choice, or else we need to think in terms of other types, with, for example, double sideband and suppressed carrier or large carrier. Okay, so this one, as I mentioned, audio signal, voice, and music will be perfect to use this type of filter, which is sideband filter. Okay, so another technique in order to generate, we call it phase shift. All right, phase shift technique. In phase shift technique, this is the modulating signal. All right, phase shift by 90 degrees. So cosine, if phase shift by pi over 2 will result in sine. This one actually we call it m hat of t. This one actually in mathematics we call it Hilbert transform. All right, or Hilbert function. And this one we have the what we call it, the carrier generator, cosine or sine. All right, multiply by this one, and another phase shift we generate cosine multiplied by this side, and after that we need to do summation or adder. Okay, so let's have a look to mathematical representation. I think we have some more minutes. All right, so if the baseband signal m of t is cosine omega t, then the output of balance modulator or multiplier will be yes, just only 1 minute. 1 minute, all right. So a sub c m of t cosine omega t, this one, all right, multiply by carrier, and this is the if we multiply, taking the relation again, the upper side, this one here we have sine multiplied by sine, then sine multiplied by sine, same will be half cosine minus cosine plus, then at the end we need to do summation. This one will be a sub c, this is lower side, this is plus minus upper side. So if we take the minus, if we said m of t cosine omega c t minus m hat of t sine omega c t, we will choose only upper sideband. And if we take plus, all right, we will result in lower sideband. All right, so either this one lower sideband or upper sideband, the output from this what you call it, the phase shift. All right, if we take the positive, we'll reach to lower. If we take the negative minus, we will have the upper. All right, and definitely this one, as I mentioned here, is less popular because it's also we have some will cost, in terms of cost, will be much higher compared to the filter technique. Okay, in terms of demodulation, we have single sideband multiplied by the carrier. We have low pass filter. Then I generate the mathematical formulation here for you. All right, you can refer to the slide. I will upload the updated one. I solved this one for you. Okay, then you can track, which is not difficult. Okay, you multiply, and for relation, the relation I have written here at the bottom. Okay, then the output of low pass filter will be the original signal, then it's a demodulation. Okay, again, this one I will leave it to you as a self-study. The vestigial sideband. All right, it's a self-study, it's not difficult. Okay, the remaining is just comparison, and I think we have done with this chapter. And for if you don't have any question, then you can leave. And I need only students that they have quiz today. I need to discuss with them about the timing. So please, students, those, I mean, if you don't have any question, you can leave. I need
Sir,
yes.
so
Have a
why
good
your
day, sir.
PC's clock is always incorrect? I've been watching it for past 2 weeks. It's
Sorry, Harish. Please, could you come again, please?
Sir, your PC's clock, it's 4:26. It's always incorrect.
It's Kuala Lumpur time.
Oh, but it's not always Kuala Lumpur because sometimes it is like 2-3 hours ahead or behind. You know, it keeps changing.
Yeah. Okay, Harish.
Okay, okay. Thank you, sir.
All right, thank you. Okay, guys. So for those who have a quiz, Ahmad, Shalom, Mardin, Land, and Avan, and also Ahmad Naif. So we have 6 students. All right. So
Yes.
Ahmad Naif and Mardin and who else said that would like to, I mean, do the quiz at 6 p.m.
At
Sir,
6?
sir, we have a class at 4:30.
You have
So
a class at 4:30.
yeah.
All right. So I mean,
Sir,
yes.
also I have a class after this one.
All right. So let's say at 5 p.m. Ahmad, Hassan, and Balant will go for a quiz. Am I right?
Yes.
The remaining at 6 p.m.
Yes.
All right. That's fine. Okay. Thank you.
Bye.
Thank you.